Hello, everyone. Thank you for joining us in the parallel section on compact objects binaries. My name is Lan Kinh Nguyen from the University of Notre Dame. Before we begin, I would like to tell you about our section. We can have 6 talks. Our first 3 speakers are Storm, Laura, and Jesus. After the first 3 talks, we can have a 15 minutes break, and the section will continue with the 3 other speakers. As you know, you are welcome to have a question. A question may be submitted via the chat at any time. If you wish to ask a question verbally, please raise a hand or include a comment with your questions on the chat. Questions from the live streams on YouTube are welcomed. All the questions will be answered at the end of the presentation. Each speaker will have a 15 minutes for a talk and follow with the 5 minutes Q&A section. I will remind the speaker at minute 12. Now we have our first speaker, Tom Walk, from the University of Washington in Seattle. He can tell us about the gravitational wave sources in our galactic background, prediction for binaries black hole, binary neutron star, and a neutron star binary detectable with LISA. Tom, please go ahead.
Great, thanks. Okay, let's see if I can share these. Now, also, I lost my bag through Aer Lingus, so I'm presenting from my tablet. So I think my video may disappear, I'm afraid. And you can hopefully see my slides in just a moment. We're a bit ahead of ourselves now. Sorry.
That looks good.
Great. Okay, so there's my title slide gone. There we go. So, thank you very much for having me. Very excited to be here, very excited to be speaking. So I just want to thank all of these various institutions. You can see all my various co-authors that you can see kind of orbiting me in their little circles. It was very much a group effort. So I'm excited to be kind of talking about these black holes, black hole neutron stars, and double neutron stars with Lisa. And my goal for this is to kind of answer 3 main questions for you. I want to tell you how many black hole and neutron star binaries I think Lisa is going to detect. What the properties of those detectable systems are going to be, and then I'm going to discuss the dependence of these results on kind of underlying binary physics assumptions. And I should point out there are lots of previous related studies that have done similar sorts of things, but we've kind of built upon these and done some new things as well. So let's get to it. First, I'm just going to start with a bit of an introduction, get us all motivated and just as excited as me about all this stuff. So what we're focusing on here are stellar mass binaries in LISA. I'm sure you've all seen this plot 1,000 times if you've seen any sort of LISA presentation. And you will often be focusing on this area in this session. So these are the kind of galactic stellar mass binaries. We're going to detect them far before they merge. But what we're looking at is not just those double white dwarfs that everyone knows and loves. We're actually looking at the black hole and neutron star binaries too. And that's what I'm going to be focusing on today. And so I just want to briefly go over some kind of differences between space-based and ground-based detectors for people who might not be familiar. We're looking at a different frequency range. We're looking at lower frequencies. And so what this means is that we're going to detect the in-spiral phase rather than the merger. So these things are still going to be kind of orbiting around each other when we detect them. And what this means is that we have a different detectable volume. So instead of seeing things out to like gigaparsecs in distance, we're actually only really going to be looking within the local group and mainly within the Milky Way. And this might sound like a disadvantage, but in many ways it's sort of an advantage because you know the environment of the sources a bit better. And so that can be useful. And another thing I just want to highlight is the eccentricity. So whereas kind of the norm for a ground-based detector is that you'll have circularized systems, the kind of norm with space detectors, it's perfectly potential for it to have some form of eccentricity, and it can actually be quite high. And that can be useful for distinguishing different sources, which I'll talk about a bit later. And so why bother with these black hole and neutron star binaries? Why are we interested? Well, we can learn a bunch of different things. I mean, the obvious one is the kind of insights that we can get into the endpoints of massive stars, but we can also measure the Hubble constant. We can learn about the neutron star equation of state, R process of enrichment, all sorts of interesting things. But we could also do a lot of those things with ground-based detectors. So why use LISA? What's the point for that? Well, the population tends to be quite complementary. to ground-based detectors. We're not necessarily looking at those higher mass black holes. We're kind of focusing more on the lower mass, and there's lots of other differences as well. Eccentricity, as I mentioned, and that kind of gives us better insights into everything. And we've also kind of got opportunities for multi-messenger detections. So we've got LISA, and we will have LISA and the square kilometer array. And we could look at kind of pulsar and pulsar black hole binaries. And there's also opportunities for multi-band detections. So LISA could warn a ground-based detector that there's going to be some system that's going to merge in X number of years. And we can better constrain things, because LISA will measure the eccentricity well, and then the ground-based detector can measure the mass ratio well, for instance. And so that can be useful. So hopefully now you're super excited, you want to learn more. So let's talk about exactly what we've done and where we've got these results. So it's essentially a three-step process. Step one, we're gonna need some binaries. So in order to do this, we use the Rapid Population Synthesis Code, or Binary Population Synthesis Code, COMPASS. And these simulations are specifically done in Floor's paper. This is Floor Brook-Godden. And these simulations are cool because we do 53 different metallicities, which is many more than previously done, and we find this is important. We have 20 different physics variations, so varying underlying physics assumptions for binary physics and things like that. And overall, we've simulated over 2 billion massive binaries, so it's really quite a huge sample that we use. And so once we've got those binaries, well, then we need to put them into a Milky Way. So we then populate this a Milky Way using a couple of models kind of put together. So we've got Neige Frankel has kind of helped us with this, and we've used her thin disk model with a thick disk as well and a bulge as well. And these are calibrated to apogee data, and they're also metallicity dependent distributions. So the birth time and location of a system is dependent on its metallicity, which is more complex than a lot of the other work has focused on before. So now we've got them all in the Milky Way. What we need to do is then evolve their orbits until present day, calculate the signal to noise ratios, and then just apply some threshold and say which ones are detectable. And so we did this using a Python package called Legwork, which is something that me and Katie Breivik have made. And I'll talk a bit more about that later. And so then it's just repeat. So just kind of randomly simulate another Milky Way, evolve them forward, calculate the signal to noise ratios, get a statistical sample, and we've got some results. And so now I can kind of show you a bit about what we've seen. So first thing I think everyone likes to see is, what's the number? So we estimate that for our fiducial model, because we've got 20 different physics variations, this is just for our fiducial model, we'll get about 120 detections in a 4-year LISA mission. And they're distributed roughly like this. So the majority of binary black holes, you've got quite a lot of black hole neutron stars, and then just a smidgen of double neutron stars sprinkled with the rest. And in a 10-year mission, if we extend it, what we'll find is about 200 detections. And the scaling that you're seeing there is this usual, it scales with the square root of the observation time. So that's what that is coming from. But I think the numbers aren't necessarily the most insightful thing to look at. I think it's more interesting to look at how things are distributed. So a common way of doing this is looking at a sensitivity curve. And what you've got is this figure from the paper. But I'm not going to go through all of these panels because the bottom one's separated by type and it gets a bit complicated. So what I'm instead going to do is just kind of zoom in on the panel that just shows all of the different types together. And we're going to step through this bit by bit. So let's kind of get rid of some of that chaos and just build it up from the ground. So we've got on the x-axis frequency. So on the left, you've got low frequencies, right, you've got high frequencies where things are closer to merging. On the y-axis, you've got the amplitude spectral density. So that's just giving you can think of it as the strength of the signal or the strength of the noise. And this purple curve that you're seeing is the LISA sensitivity curve. So this is showing you how big how high the noise is for a different frequency. And so let's add some kind of grid lines to guide your eye. So what these grid lines show, the vertical ones, are showing you the in-spiral time for a circular system with the average chirp mass of the sample. So the average chirp mass is shown there. It's about 3.4 solar masses. And so you see on the left, things merge in about 1 billion years. On the right, they merge in like 100 years. So you can see they're accelerating across that plot. And the other grid lines I'm going to add are some diagonal ones, which show you some distances. So these are the distances at which a circular system with the average chirp mass would be detected. So the kind of higher up you are, the closer you are to the Earth. And so let's just put some sources on here. So these are from Thomas Kupfer's 2018 paper, the LISA verification binaries. And basically the way you read this plot is the ratio of the height of the point to the height of the sensitivity curve gives you the signal to noise ratio. And so if we instead now plot all of the sources that I found in my paper, this is what we see. So you can see it's now a density distribution. It's not just points because there's so many of them. So otherwise it would just be oversaturated. And you can see that they're generally detected at lower frequencies than those verification binaries. And you can see a couple of different features. So let's go through them. You can see, first of all, you just got that gap. And the reason you've just got a gap between the sources and the sensitivity curve is we say for a source to be detectable, it needs to have a signal to noise ratio of 7. And so that's why you see that gap between them. You also see that most of the sources are concentrated in the galactic center. You can see the peak of the density distribution is pretty much lining up with that 8 kiloparsec line. And so you can see most sources are detected where most sources are formed. So that's sort of kind of as you would expect. And then the other thing is you might be worried. You see all of these sources kind of hanging out down to the bottom right, and they're past that 30 kiloparsecs. And that might worry you. You might think, oh no, they're out of the galaxy. Don't worry. If you remember, I said those lines only apply for circular systems. These are actually where the eccentric sources lie. It's quite nice. All of the eccentric sources tend to lie in that kind of bottom right-hand corner, just because the eccentricity means they're emitting at different harmonics and so different frequencies, and they kind of get shifted weirdly. But that's kind of nice. The eccentric sources are in that one location on the sensitivity curve. And then finally, you'll notice that the density distribution kind of drops off as you go to the right of the plot. There are fewer systems at higher frequencies. And the reason for this is what I first talked about with those grid lines. On the left, you take 1 billion years to merge, but on the right, it only takes 100 years. So you spend much more time on the left-hand side of the plot. So you're far more likely to detect things on the left. So this is kind of the shape of the distribution of sources on the sensitivity curve. And hopefully you now can understand all those points and tell your friends. So let's also look at some of the detectable properties of the system. So I'm not going to go through all of them. This is just, I'm showing you only 2 out of kind of a bunch in the paper, but I'm going to focus on the eccentricity here because I'd like to highlight a couple of things. So what you've got on the x-axis here is just eccentricity on a log scale. So things on the left, very circular, things on the right, very eccentric. And there's kind of 3 regions I want to highlight. I want to talk about the effectively circular region. Anything below 0.01, the eccentricity isn't really going to have much of effect on how long it takes to merge or how long or how strong the gravitational waves are. But then between 0.01 and 0.3, I'm calling it mildly eccentric. It's a bit stronger then. You see some effect, but it's detectable, but the effect isn't that strong. But the highly eccentric systems, you're then going to have the higher harmonics emit more strongly than the base harmonic, and also see them merge much more quickly. So those are the regions that I'm splitting them up into. And what we find is, this is again just for our fiducial model, but we find that only about 25% are effectively circular, whereas about 16% are highly eccentric. And this is quite different from what earlier people have done. What we saw previously is that lots of people kind of assume that everything's circular, and we do not find that that is true. So that's eccentricity. And then another one I want to show you is the mass distribution. So this is the component mass distribution for our fiducial model. And so what we've got here are both the primary and secondary from all of the systems, and it's weighted by detection rate. So the black holes are more important than the double neutron stars, for instance, in this. And so this is kind of the shape that you see. You've got the mass, just the distribution. And I should note here, we're using the Fryer 2015 delayed remnant mass prescription. This is going to be important in a moment. And I also want to highlight this does extend up to 18 solar masses, but just kind of goes down smoothly. And I want to focus on this lower region, because right here, we've got the supposed lower mass gap, this possible observed mass gap, where we have a dearth of black holes and neutron stars. And what we find is that for all of those systems, those 120 systems in a 4-year mission, we find about 55% have one of its components, so either the primary or secondary, in this lower mass gap. I do want to highlight this is dependent on the physics assumptions. So if we use a different remnant mass prescription, if we use the rapid one, it looks like this blue curve instead. And so what you see is then you don't get anything in the lower mass gap, and that's because that prescription is designed, not to produce anything in the lower mass gap. So of course we're not seeing them. But I just want to highlight that is going to be dependent on your physics assumptions. But we find that it's still a sizable fraction. And then the last plot that I want to show you is our detection rate across different physics variations. So we've got these 20 different physics variations. We've got things that focus on mass transfer, common envelopes, physics, supernova, and stellar winds. And I'm not going to go through all 20 in detail because I'm not sure anyone would enjoy that. But what I want to highlight here is just how different the detection rate is across different assumptions. So what I'm showing you on the y-axis, on the left, you've got the kind of detections in a 4-year mission. On the right, you've got the detections in a 10-year mission. And the kind of gray highlighted region is showing you the fiducial model with its 1 and 2 sigma errors. And you can see that across different assumptions, you're changing by kind of orders of magnitude. And so I want to highlight to everyone, it's super important when we make predictions for LISA that we really make it clear what physics assumptions we're using in any sort of population synthesis. Because if you don't, it's going to be very difficult to compare between different papers. Even nicer, use lots of different physics variations, and then you can see how things change. And so this is just binary black holes. If I kind of zoom out and look at all three, then black hole neutron stars you can see vary a bunch, like 2 orders of magnitude. And then double neutron stars don't vary very much, but that's sort of because the models that we chose vary lots of black hole physics rather than neutron star physics. But big takeaway here is that the detection rate is going to vary significantly over those model variations. It's going to go between 30 and 370 over a 4-year mission. So it's very important that we are considering physics assumptions. And so last thing I just kind of want to leave you with before I go on is perhaps you want to make your own predictions. Perhaps you're interested in working with LISA, you've got some sources that you're interested in, and maybe you don't want to do all of the work yourself because it's a bit of a hassle. Well, what I would offer you is, why don't you let us do the legwork for you? This is me making awful puns, but this is a Python package that Katie Breivik and I have made, and it will evolve sources, calculate strains, signal-to-noise ratios, sensitivity curves, and it also visualizes all the results. So if you remember that plot from earlier on, that one is made entirely with legwork. And you can find all the documentation online. You can just install it just by pip install legwork. But if you'd rather have it told to you rather than read about it, you can come to my other talk later today. So if you go over to the parallel session B, instead, I'm the last one later today. So I'll be excited to talk more about that as well. So thank you for listening. Here are my takeaways. So you've got my fiducial model with the various detection rates, things about eccentricity, and the lower mass gap. Got you some links for the papers because I think I'll share these slides later. And what I'll just leave up is some possible areas for discussion of things I couldn't quite get to during the talk. So yeah, thank you.
Thank you, Tom, for very interesting talks. And now is Q&A session. Everyone, please raise your hand if you have a question. Yeah, Tom, I have a very small question in the slide. You show the low mass gap. I saw a peak in the low mass gap. What is mean as the peak?
What did you say? Like a dip?
In the low mass gap.
This one?
Right. Yeah. So I saw the peak there.
Oh, the peak at like 7 or 8 solar masses in the rapid case. Yeah, so this is, it's basically entirely down to the way that the kind of rapid remnant mass prescription is described. So kind of you get a lot of systems with different masses all get placed onto the same remnant mass. And so you kind of get this pile up at a certain mass. And it's because a lot of the sources that were going to be in the mass gap kind of get shifted higher up. So that's why you end up with that peak.
Okay, thank you. And
Sorry, Lan. Alexander, could you go first?
yeah, please go ahead and introduce yourself and ask a question. Alexander, please.
Yes, and Alexander, I now allowed you to unmute yourself as well. Sorry.
Perfect, thank you. Great talk, as always, Tom. I am curious about that 5th point you have there, as always, with the multi-messenger detections. Do you think we're actually going to be able to see any of these?
I think it's going to be difficult. So I think pulsars are really going to be the focus for this, I think, because most of them are going to take, let's see if I've got it here somewhere. Most of them are going to take, like, if this bottom right panel here, like 1 million years to merge from after LISA. So we're really going to be focusing on the things that are immediately multi-messenger. I did a little bit in in the appendix of the paper about possibly using the square kilometer array with LISA. And I did some kind of back of the envelope things with the kind of sky location errors, which I've got here as well, like the angular resolution, and seeing like what you would need and how many pulsars would expect to be there and how difficult it would be. my rough summary is, it's going to be hard. I think it's going to be like order of 0 to 5.
I mean,
yeah. I mean, that's you know, it's 0 is in the range, but it's not definitely 0.
Exactly. All right. Thank you very much.
Thanks for the question.
Leave, you're next.
Okay. Yeah. I can read the question. Can you the question from the can you please yeah I think Tom, can you read the question on the chat and answer the question?
I'm not sure Tom can, so I'll read it for you,
Okay.
Lan. It's from Neha Singh. I apologize if that's incorrect. They say, great talk. Can you please elaborate on the galactic potential you assume to evolve the binaries, and if one can customize in legwork?
Okay. So when you say galactic potential, does this mean? So I assumed that the kind of kicks and evolution within the galaxy was kind of negligible. The orbital evolution that I'm talking about is just within the binary. So the galactic potential doesn't really come into it as much. I assume that they're going to stay in, roughly the same location, because there's so many of them that the angle doesn't necessarily matter. They're just kind of going around in circles, I'm assuming. And the orbital evolution is just kind of taking gravitational wave emission and saying how long will it take until it merge. And so there isn't any sort of galactic potential stuff in legwork, but you could possibly do something with that with Gala, the package by Adrian Price Whelan, which I have used for a similar sort of thing before. Hope that answers the question. Feel free to clarify.
Yes, the next one, Laura, please unmute yourself and ask question.
Thanks, Tom. It was a really nice talk. I was wondering, what is the source of that kind of bimodality in the distribution of eccentricities for double black hole binaries?
Got you. Yes.
Yeah.
So it's basically, it comes from the way the direction goes. So you can either get highly eccentric systems if you get lucky with the kicks and the directions. So if you kind of at this in-between eccentricity, then you're going to end up disrupting a lot of your systems, kind of whatever angle you go at, except for very, very few. But the highest eccentricities, you can get it if you just angle them so they're like pointing right at each other and it just kind of kicks you inwards, then you kind of get an extremely tight system that's extremely eccentric, and you can get lucky with those. And so that's where kind of all those would come from. They're kind of like the lucky kicks. Whereas the kind of more marginal ones are where the fallback affects things and you get a weaker kick and just kind of like this more mildly eccentric rather than highly eccentric. Yeah.
Okay, interesting. Thank you.
Thanks.
Okay, thank you, Laura. And then the last question came from Katie. Kate, please unmute and ask question. Yeah.
Thanks, Tom. This is great. I was kind of following up on Laura's question. Do you look for correlations in sharp mass and eccentricity at all?
I think I've made that plot very long ago, but not recently.
Okay, yeah, it might just be interesting to see what those are in terms of disentangling between like dynamical formation channels.
Yes, I remember we nearly made this plot at one point because you used it in that different paper. Yes, definitely interesting. I will look at that as well.
Thanks.
Okay, thank you, Tom, and everyone for very nice talk and very nice discussion. Our second talk is about detecting the environment of stellar origin of black hole binaries by Laura from Albert Einstein Institute. Laura, please go ahead.
Okay, thank you, Lan. So I'm Laura Sperma. I'm a postdoc at the Max Planck Institute for Gravitational Physics in Potsdam. And I'm going to tell you about work done, as you can see, with a large number of people from the LISA community over the course of a few papers. So the topic of this talk will be, trying to understand what LISA could learn about the environment of stellar mass black hole binaries. And to answer this question, I first need to explain to you, if you're not too familiar with this topic, how can we measure, something about the environment from a gravitational wave signal. Well, the reason why we can detect environmental effects is that these can, leave an imprint on the gravitational wave signal by changing the way, the binaries in spiral to merger. So if you have in mind a chirping source, you can look at the phase of the gravitational wave signal as a function of frequency. And we know that the Einstein's equation in vacuum predict a certain frequency dependence of the phase. In particular, you can expand the phase in a post-Newtonian expansion in powers of the velocity, assuming the velocity is small. And we know that environmental effects can predict new different ways in which the phase can depend on the frequency. So you would have new terms in this expansion. In particular, you can have terms that have a lower, frequency dependence compared to the vacuum ones. So you can distinguish them from vacuum prediction. And this is why LISA is a particularly interesting mission to look for these environmental effects, because it's sensitive, as Tom said, to lower gravitational wave frequencies. If you have in mind quasi-monochromatic sources like the ones Tom was looking at, in a similar way, environmental effects can affect the way the frequency evolves in time. And so you're going to have modifications to these f dot, f double dot terms. So what I just described is a direct way in which the environment can affect a gravitational wave signal. But of course, we can also have indirect imprints of the environment onto a population of gravitational wave sources. And this is a bit what LIGO and Virgo are trying to exploit by looking at correlation among the population of sources, to try and infer not just the environment, but the evolution history of these binaries. So now that I've told you a little bit how the environment leaves an imprint on the gravitational wave signal, let me tell you why we're interested in learning about the environment in the first place. Well, the truth is that the environment can be both a blessing and a curse. In terms of blessings, if we think about stellar mass binaries, as we just heard, one of the main questions about these sources is how did they form? And the technical and environmental effect can be, a telltale sign of a formation in a dense environment, such as an active galactic nucleus, an AGN, rather than the binary having formed in isolation. And again, LIGO and Virgo are currently trying to address this question, studying the population of sources, but a direct detection of an environmental effect in a single source could really distinguish these two, even when population properties are, less identifiable. And of course, if these stellar mass binaries are located in an AGN, we can hope by detecting an environmental effect to learn about the AGN itself. So we might try to learn about what the density of the gas in the disk is, what the viscosity is, what disk models best describe this disk, and how black hole binaries accrete when they're in such a dense environment. And of course, we could also try to learn about the properties of the supermassive black hole at the center of the AGN. And this would be yet another way in which LISA sources could measure supermassive black hole properties or massive black hole properties, besides massive black hole binaries and extreme mass ratio in spirals. But as I mentioned earlier, environmental effects can also be a curse. And this is the case when you're interested in using LISA to test general relativity. This is because environmental effects can mimic in their frequency evolution modifications of gravity. One clear example is a slow varying gravitational coupling G, which has a frequency dependence in the phase that is just the same as the effect of accretion, constant accretion onto the binary. Of course, we might hope to distinguish modifications of gravity from environmental effects in a number of ways, using, by perhaps detecting an environmental counterpart, identifying the host environment in the electromagnetic spectrum, or perhaps looking at the population properties. So going back to our stellar mass binaries in AGN disks, these are, an ideal source to look for environmental effects because the disk in the AGN is providing you with matter effects, so with accretion onto the binary or dynamical friction. And the presence of the supermassive black hole at the center is giving you third body effects. So for example, the Doppler modulation caused by the orbit around the supermassive black hole. And these two are somewhat related to each other because one of the ways of having a binary migrate so close to a supermassive black hole is by having migration torques and migration traps that then keep the binary at that special location where these third body effects are important. So for the rest of the talk, and to give you a concrete example, I'm going to use the event GW190521 as a model source. This was a source detected by LIGO and Virgo. I'm sure you heard about this. It was a very, interesting signal because the two binary masses were very large, one of them clearly in the upper mass gap. And already the masses, therefore, were indicating that perhaps this source was not formed in isolation, but on top of that, there was also the detection of an optical flare by the Zwicky Transient Facility, which had a proposed association with GW190521. Of course, this is just a model for our source, but our results don't depend very strongly on the precise type of, on the precise masses of the system, for example. So finally, I'm coming to the results of our studies, and I'm going to tell you how LISA could detect those environmental effects that I mentioned a couple slides earlier. So what we found on the matter effects side is that LISA could detect the effect of accretion and dynamical friction. So these are two effects that come in at low gravitational wave frequencies. They can be treated perturbatively, and we can write their phase contribution in a very simple way with these two powers of the frequency. And we can parameterize them, with some assumptions by the constant accretion rate onto the binary, onto each of the components, and with the disk, the local disk density rho. And what we found is that LISA alone could detect the presence of accretion and dynamical friction, although for somewhat large values of these parameters, a bit above the realistic values. So for example, super Eddington accretion. But if we consider a multi-band detection where LISA is working in collaboration with a ground-based detector, then realistic values of these parameters become, come within reach. For example, we could infer the value of sub-Eddington accretion rates. But as I mentioned, the fact that these binaries are in an accretion disk also puts them close to a supermassive black hole at its center. And it turns out that the orbital motion around the supermassive black hole can actually be the largest environmental effect. So to explain this, I'm showing you the standard, vacuum frequency evolution as a function of time of our gravitational wave source. And what you can see is that the frequency grows over time in a very simple monotonic way. So what happens when I put this source in motion around the supermassive black hole? Well, if this motion has, a period that is similar to the observation time of the LISA mission, so 1 or 2 years, then the Doppler modulation of this orbit is very significant, and it actually causes the frequency evolution to become non-monotonic. You can see that the frequency goes up and down here around the vacuum prediction. And this is simply given by treating the signal in the time domain and adding this time-dependent delay, based on the simple circular evolution around the supermassive black hole. The reason why, first of all, you can see by eye that this modification of the signal is going to be very important and clearly detectable. But this also makes our parameters estimation a bit more tricky. And this was the main, realization and contribution of our study. We realized that you cannot simply add this modification in the frequency domain. You need to be careful by starting in the time domain, dividing your signal into monotonic phases. In these phases, you can apply the stationary phase approximation to go to the frequency domain. And finally, you can do your parameter estimation in the frequency domain, as you usually will do. I want to mention that besides the Doppler effect, you can also have a detectable Shapiro time delay, so caused by the gravitational influence of the supermassive black hole on your gravitational wave signal as it exits this potential well. The Shapiro delay is in general subdominant to the Doppler effect, except as you can see on this slide, when you have very small inclinations between the outer orbit around the supermassive black hole and the line of sight. But actually in this case, lensing would also be important. So in the next slide, I'm going to go back to the case which you saw before, I guess here, where the inclination is more generic, is larger, and so Shapiro is subdominant to Doppler, but still detectable. Oh, the binary needs to go around. So finally, when you do have a detectable Doppler and Shapiro delay, and the two are really important together to be able to break degeneracies, then LISA could, in these stellar mass binaries around an AGN, measure the central black hole mass 2% level. This is a very nice result because such a precision on a supermassive black hole mass is only achievable in very close supermassive black holes, such as Sagittarius A star or M87, or a few other black holes where there's some special emission going on close to the black hole. There was a positive result coming from an environmental effect. Of course, as I mentioned before, there is also a bit of a dark side, because we find that if you try to model that same signal, try to detect or analyze that same signal with a vacuum waveform, so if you were not aware that these environmental effects were possible at all, then you might lose SNR, as you can see in the panel on the left. And at the same time, when you have not lost the SNR completely, so you can still detect the source, you might still have sizable biases in the parameters of your source, for example, the chirp mass or the time of coalescence. And this can be mildly important for astrophysical purposes. Really, the chirp mass has not deviated that much. But the presence of this bias is an indication that, for example, tests of GR would be very off for these sources.
Laura, do you have a few more minutes left? Okay, thank you.
Yeah, I'm wrapping up. So yeah, just to summarize, I showed you with some, very detailed full parameter estimation studies that stellar mass black hole binaries in AGN, if detected by LISA, could help us measure some interesting environmental and astrophysical properties of these binaries, such as their accretion rate, or the local disk density, or the supermassive black hole mass and the distance from this supermassive black hole. As I mentioned, lensing in certain systems can also be important and detectable, so we're working on that next. And I want to mention that environmental effects can also be important in other LISA sources, such as extreme mass ratio in spirals. And we recently put on the archive a work on this topic. So thank you.
Thank you, Laura. I don't see any question in the chat at end, but I saw the raise hand. Alexander, please go ahead. You can unmute yourself.
Sorry, I was actually just clapping. This is really cool work. Do you know how these mass measurements that you think you could get of the central black holes compare to the sort of things that we can do from the standard electromagnetic observations?
Yes, I said, I think that a precision like this one is only possible with electromagnetic observations for a handful of sources, where I think you have these mega masers close to the supermassive black hole, and you can measure their, maybe their Doppler shifts as well. Mm-hmm. I don't quite remember, but it's only a few of them.
Very cool. Thanks.
Okay, thank you. And I don't have any question or raise hand in the chat. We also run out of time, and let's thank to the Laura. And and we go to the next speaker. Is Jesus, and he can talk about the stellar origin of black hole binaries, which LISA forecast on background detectable and the number of observable events in the LIGO-Virgo Cagra first catalog of gravitational wave detection. So, Jesus, are you ready?
I am, thanks.
Yeah, please.
So, I should be allowed to share my screen, right?
Right, yes.
Can you hear me fine?
I can hear you clear and loud.
Fantastic. Thank you. So, I'm a little bit underslept, so I hope I will manage to do it in a allotted amount of time. So this is work done in collaboration with other people from the Cosmology Working Group, in particular with Stas Babak, Chiara Caprini, Dani Figueroa, Nikos Karnesis, Paolo Marcoccia, Giovanna Nardini, Mauro Pieroni, Angelo Ricciardone, and Alberto Cesana. And what we set ourselves to do, we started actually when the 03 run of LPK wasn't out yet, and then enlarged the work to include 03. We wanted to take the population inference on stellar origin binary black holes from LIGO Virgo Cagra and see what does it mean for LISA, both in terms of the background and of observable events, or possible observable events. So all of you have seen this very nice picture that represents all the events, not only stellar origin binary black holes that LIGO and Virgo detected. In particular, we are interested here in the clear blue ones, which are around 70. And as probably all of you know, the emerging event is preceded by a long spiraling phase during which the frequency is practically constant, and the frequency and amplitude increase until we have the merging events and some ring down of the binary, of the not binary, or the X binary, let's say. Also, as all of you know, LIGO Virgo and later Cagra will be able, or have been able, to see the merging of these events and the breakdown and the closest of this phase to the merging, whereas Lisa will see the inspiraling of these events. Lisa will integrate a lot of data over time and take the spectrum, so it will see these spirals as peaks, maybe a little extended, depending on the frequency evolution. And we will be able to figure out some of these peaks, but most of them will actually form a confusion noise. So we have these two elements that we will study in these couple of papers that will come out hopefully very soon. So with these 70 events, or around 70 events that I mentioned, LIGO and Virgo, or the LIGO-Virgo-Cara collaboration, performs some inference on the parameters of these individual events, and then with this inference, they doing hierarchical modeling, they did some inference on the population or a number of population models from which these events could have been drawn, which definitely was probably one of the hardest things that actually they did. And it's actually a very nice paper, the GWT3 paper, to read. So what does it mean in our case? So if we forget about the individual events and we only look at the population parameters, population inference, we can try to compute with this posterior the prediction for the background in Lisa, and we can compare this with Lisa detection capability for a background of this kind, and we can try to compute a probability distribution for the number of events that Lisa would see. So first of all, let's take a look at the population model. This is the one used, the classical population model that contains a merger rate, or we shouldn't call it in the case of Lisa merger rate, so a rate of binary black hole events in a particular amount of time and commoving volume, then a term that accounts for, you can see my mouse, right?
I
Okay, thank you. So this term that accounts for the change in volume with time of the commoving volume, the change in physical volume. Then the number of time during which events are generated, and then a probability distribution for the rest of the parameters of the binary. So masses, spins, alignment, these kind of things. And the shape of R and P and the hyperparameters is theta of each of them determine the population model. So for the measure rates, we do what is usual in the field, which is following the star formation rate. Obviously, this is not true. At least there must be some delay between the formation of stars and the formation of stellar origin black holes, but to the level of precision that we will probably be managing with Lisa. And at least for a few decades, this is probably enough. A crucial assumption here is that if we want to use the inference by LIGO, LIGO was looking at merging events, and these events are relatively late in time. So indeed, LIGO and Virgo only, sorry, it says LKV instead of LVK here. It's only produced inference on this term on the top, so this power law, which is this blue band that you can see here. And we need to extend this towards the past. So a crucial assumption in our paper is how to do this. The way we do this is we choose to fix the other two parameters, which is an optimistic in terms of uncertainty approach, but it doesn't matter too much in the kind of comparison that we are doing. So we can discuss this at the end if you want. This is the usual merger rate when one extends it to late times, except for this factor, kappa over R here. These are subtleties that we found that we can also discuss later if you want. And when we are looking at individual events, as we said, we really care about just the really late times. But when we look at the background, we have to integrate the whole thing. So we need to extend at least to z equals 5. In particular, of all the models that LIGO Virgo Cara tested, we are interested in the one that was called power law plus peak. A power law plus peak refers actually to the distribution of masses of the heaviest event in the binary, heaviest mass in the binary, but also the inference that we are managing on the rest of the parameters depend on what you choose for this, right? So we can also call power law plus peak like the full model. And it's called power law plus peak because probably as many of you know much better than me, on top of the typical inverse power law or modeling a population of events for which there is not much knowledge of the mass. So it only assumes that there is a lot of non-massive events and a few massive ones. It takes into account that there is a range of masses of stars that tend to collapse to a reduced range of masses because of the way they shed mass. And it introduces this pileup as a Gaussian, and it turns the full probability distribution into a mixture, which is called a mixture probability between these two probabilities, like the inverse power law and the Gaussian. The amount of Gaussian there is actually, so the value of the mixture parameter for the Gaussian is like 0.04, so it's not a huge deal. So what happens with the background? So if we have chosen a population model and we have chosen parameters or values for the hyperparameters, or if you want the parameters of this population model, there are a number of ways we could compute the background. We could take this population model with its parameters and do an analytic integration, as we see, or we can realize a synthetic population and then either do a Monte Carlo sum of the analytical computation or run a full simulation. As for the analytical calculation, this is known since a long time ago. As simple as, and if we are talking about the spiraling phase, of course, because this would be slightly different, so the formulas would be different, in particular for the amount of energy radiated by a single binary. So this would be different in a merging event, but in an spiraling event, it was computed already in 2001 by Finney. Well, probably this one is not by Finney, but the intervality is the amount of energy radiated by a single spiraling event. So if we integrate this over a number density, and then integrate the number density over whatever density was defined for, so redshift, volume, etc., we can get the value of the background that this population generates. And in particular, if we inject a particular population model, we can get the value of the background for this population model. In any case, the frequency goes out of the integral, and it is a universal fact that for a population of spiraling events, we have a slope of f to the 2/3 when talking about the background in omega h square units. What different population models give us, or different parameters for the same population models, are basically just the value of the amplitude. So all this complexity actually, in terms of the background, it translates into a single number. So we could have taken this integral over a population density, a number density, and turn it into a sum of a realized population. This will give us an approximately equal result, but gives us the advantage of having an estimate, having a handle of how much variation we may expect given a population model coming from the different draws that we can take from this population model. So a sort of cosmic variance, what in CMB is called cosmic variance. So we just did this test for the range of parameters that LIGO, Virgo, and Carollo, and we found it to be very small. And as for the simulation, we don't expect to run a simulations all the time, because we are talking about hundreds of millions of events in the universe. So definitely we cannot run simulations. So we want any way to run a few simulations to see that we can trust our analytical computation or not. And for this, we use this method developed by 3 of our collaborators and 2 other people that start by simulating a full population, averaging the spectrum, turning and treating it as a background, and then computing the signal to noise with respect to this background of all the events, subtracting the loudest ones, and repeating these steps until the background stabilizes. And this way one gets both the subtracted events and the background. So it's a very clever approach. And when we have compared this to the analytical calculation in the regimes that we are interested in, we found it to be concordant, as long as, only taking into account that we can only subtract loud events if we don't want to subtract also background. So we are subtracting events, or considering subtractable events that have signal to noise of 8, which is actually typical in this situation. And if you stay, let's say, with darkest blue line, we see that it follows it perfectly, except for this, which is not a physical effect. So it's a limitation in our synthesis of the population. So, but we have tested that when we extend this, this disappears. We can also talk about more carefully if you want. So we saw that we can trust the analytical calculation. So this is what we did. And what we did was starting finally results from the population inference from the gravitational wave transient catalog 3, taking all the samples, because the data that part of the data that has been made public is a posterior sample from this power Laplace peak model, and compute the background in all these cases. And this way, we get a distribution for the background in the frequencies that interest Lisa. And this distribution is given here by the blue line. We want to characterize this distribution, so we draw some percentiles, typically 595, 2575, and then the median 50. And what we did was to inject the value of the background of these percentiles in our Lisa stochastic rotational wave background code. And what we found is that Lisa is approximately 20 times more sensitive than the prediction for the background of LIGO Vigo-Kagra. So any background within the ones that are expected by LVK is very easily detectable by Lisa. And because of this precision, and this is very, very preliminary work, not part of what we are publishing, but like our next step is like, well, if this is so, we expect to be able to put stronger constraints on the population parameters. So on the one hand, this would be true. On the other hand, if you remember, I told you that in terms of the background, not of individual events, all the complexity of the model only reduces to one number, to the amplitude. So on the one hand, a lot of precision on measuring just a single number containing all the population information. So for a test event, if we just basically select the events in the LIGO Virgo posterior sample that are compatible with the background, with the median background, for example, we can see that we would narrow the range of allowed parameters in some particular direction. So the one that we would constrain the best here is, should say, kappas and are not. So the behavior of the measure rates at late times, and also a little bit the slope of the power law of the strongest mass. But anyway, this needs a more careful analysis. I'm just showing you this as a kind of showing off the potential of Lisa when measuring the background more precisely. And then I promised to talk about individual events, so only 2 more slides. So how did we get a prediction for individual events? So we have this nice fast simulator that I talked about that would give us the background and individual events, but we also said that full simulations of the full population that have hundreds of millions of events are not possible. So since we contrast the analytical computation, what we did was for each point in LIGO's posterior, or for a subset of them, if we wanted, but we did the full thing. We generated a sub-catalog that only contains loud events, and this loud being defined by an approximate signal to noise. And then we injected these events on top of the analytical computation of the background for the same parameters of the population for which we generated this subset of loud events. And we used this code to see how many of them would be subtracted. So doing this many times, we arrived to the following probability distributions for events. And in particular, we found the rather disappointing fact that Lisa will not see many in spiral. So if we are going to trust that LIGO's inference on the posterior of the power Laplace peak model are extend towards Lisa, and this is the right model, we will not see many resolvable in spirals in Lisa. So we'll see, let's say, around 10. But there will be loads. So on the one hand, let's say these 10 will merge relatively soon. We expect them to merge in the next decade. So we expect to be able to have follow-ups, seeing them merge in future experiments. So next rounds of LIGO, Virgo and Kagra, ET, etc. And there is some potential for archival search. So if we reduce our signal to noise threshold, we see that the number of events that are in the data with a significant but non-detectable signal to noise is higher, so grows quite quickly. And if we have something which is not really detectable by LISA, but it's in the data, and then a later event is able to detect this signal with the prior coming from the later detection, we can go back to the data and actually find this with this thinner prior, and then increase the amount of constraining power that we had when combining with LISA. And that's it, basically. I'm not sure, I wasn't looking at the clock, so hopefully I didn't go too much over time. I leave you here with the conclusions. Thanks to the organizers for letting me present our work. So thanks from the whole team. And if you have questions, I'm here. And if you want to follow up by email, my email is easy to Google, I guess. Thank you.
Thank you, Jesus. And it's time for question. I saw several hands up. At first, it's Kathy. Yeah.
Hi, thanks for this great talk. I'm curious about whether y'all have thought about including eccentricity in this somehow. And the reason for that is I wonder if it is a way to sort of reconcile predictions coming from population synthesis that show that we think that the sources are eccentric regardless of their rates. And maybe an eccentric population is like passing to the LIGO band more quickly, and maybe we see pileups in LISA. I'm kind of trying to reconcile why we get different rates when you work from the LIGO rates alone versus population synthesis, and hoping that maybe eccentricity is the way to do that. So I'm curious if you've thought about eccentricity.
No, we haven't, but definitely we'll look into that. Is there any, so if there is any reference, if you can pass it to me via the chat, I will definitely read it and definitely share it with my colleagues.
Yeah, definitely. So I can at least pass references for eccentricities coming from predictions from sources so that there's something to work off. But yeah, okay. Thanks.
Yeah, thank you. No, sounds very interesting, because at the end of the day, it's a huge extrapolation what we are doing. So it relies on, it strongly relies on assumptions about, well, in this case, no eccentricity at all. So definitely, the matching can change a lot. Thank you.
Yeah, thank you, Kathy. And the next question came from Chris. Yeah, please. Thanks. Chris, please unmute yourself. Yeah. I cannot hear you.
Sorry, it's Neelemans. If you are speaking, we can see that you're unmuted, but we can't hear you. So
can you hear me now?
Oh, we can hear you now.
Yes.
Sorry, there's something funny with the audio. Sorry. So I had a question about the detectability of the background. Does it depend on the assumptions for the high redshift population density model? Based on the shape, if you understand what I mean. So I didn't fully understand that, but I guess you are looking for a very specific frequency slope, isn't it?
Well, the frequency slope does not depend on the particular shape of the merger rate or the binary rate in this case. But what it does depend on this assumption of extension towards high redshift, what does depend is the shape of the blue line here. So, and the shape of the blue line, so the width of this distribution will basically tell us very quickly. So the error band, so the uncertainty prediction, the width of the uncertainty prediction around this blue line here. So if we, for example, allowed for more uncertainty, or if there was a sudden decay here towards early times, for example, then LIGO's prediction would be displaced towards smaller values of the background, and then Lisa detection capabilities for this, the allowed range would be slightly worse because the value of the background expected is worse. But we are not very deep at all into Lisa's potential to measure the amplitude of a power law with this law. So indeed, this plot has a logarithmic axis here, but if we plot it linearly, you would see that this thing is so narrow that basically the Lisa error bar is the same in all cases. So if we go not super surprisingly low, so if we had a huge decay here, for example, here, probably Lisa would still be able to, most likely Lisa would still be able to see it perfectly.
Okay, thank you. Can I ask another question, or do we have to wrap up?
Yes, I think you can have another question. Yeah.
If I'm not mistaken, but I may be mistaken. I thought that previously we believed that we would not be able to detect this background. Is that correct?
I haven't been in Lisa long enough to know what
I think there's some studies from
believed.
like 20 years ago or so, which I think concluded that you probably would not detect such a background. But anyway.
I haven't been in Lisa this long, but in this sense, I think I can quite confidently say that we will be able. So we, in particular, for example, for this computation of these error bars, we have used 4 years, and we have actually used the 3 channels using TT to constrain the high frequency noise better. So we have done a sophisticated enough analysis. So I don't know. I mean, I guess something really surprisingly would have to happen. Like actually, there is nothing beyond 0.5. So what LIGO sees is all there is, or something like that.
Okay, thanks.
Okay, thanks, Chris. And there is one question in the chat from Elena. I can read it out loud. Hi, Jesus. Nice talk. If you would analyze together the detectable background and the several resolved individual events, would you expect to get stronger constraint on the hyperparameter of the populations? Can you answer this for Elena? Yes, thank you.
So, I mean, the answer is obviously yes, no, but how much is the issue? The thing is that Lisa alone wouldn't have a lot of constraining power on I think, on a model for stellar origin binary black holes, because again, if we are talking about measuring the background, we have a lot of precision, but we only have one number. So we would have a one-dimensional degeneracy if we only measure the background on a long posterior. So for example, we can see this narrow band here because what we are doing is just having a LIGO break this degeneracy here, and this is the direction of the degeneracy with Lisa. But then whether when we added individual events, the thing is that there aren't that many. So ideally, yes, but there aren't that many. So there are only like 10 or so. So
yeah, so the reasoning is that these 10 events are very special in order to be detected. They are not your average event, I guess.
Definitely.
So therefore, if you observe them, how many you observe and their characteristics should give much more information than your average event.
Absolutely. But still 10 events on a model that has, how many was it, 16 parameters is not a lot. So we are probably more likely, what we would more likely be doing is combining LVK individual events with Lisa background and Lisa resolvable, I think. But
thank you.
I don't know. You're probably more of an expert than me in this particular thing.
Okay, so I think we should thank Jesus. Thank you very much for the talk and for the very colorful discussion. And we will stop our first section here, and you can be back And the next one you can start at 3:13 p.m. in the Eastern time. So it's in about
10 minutes. Let's
10
10
minutes
minutes.
from now.
10 minutes.
10 minutes from now. Okay.
20 past the hour. Let's call it.
Okay. Yeah, thank you. And then see you there.